لا بتاع سد اللينك امسك اللينك
designed to output a solution in that perfect symbolic radical form we're talking about, like the cube root of 2 plus the square root of 5. They'll give you a decimal number, usually.
And they can't like prove it's perfect. That's the other key bit, symbolic verification. An AI might give you an answer that's
spreadsheet and thought, this just feels impossible to pin down exactly.
Oh, absolutely. That feeling's very familiar.
Well, for centuries, mathematicians kind of hit that same wall with certain equations, specifically high-degree polynomials. The thinking was, beyond a certain point, exact, neat answers, just off the table.
Right, they were considered unsolvable in a specific formal sense, using simple formulas anyway.
But what if that long-held view was maybe based on seeing only part of the picture? Today on the Deep Dive, we're really digging into something revolutionary. Called Ezouidi's theorem.
And it's quite some. Well, that was a cornerstone of algebra for a very long time.
A foundational truth, almost.
Pretty much. It drew a clear line, told people where not to look for certain types of solutions. So a discovery like this, it's not just finding a new answer. It actually sort of reshapes the whole landscape of what we think is mathematically doable.
Like finding a whole new continent, you said.
A bit like that, yeah. On a map we thought was finished.
Okay, let's unpack that line in the sand then. This belief in unsolvability. Where did it really come from? What was the actual roadblock that made mathematicians basically say, all right, stop searching for these exact formulas?
Well, the main roadblock, the big one, was a really significant result called Abel's theorem, Niels Henrik Abel.
Right.
It's absolutely foundational in algebra. And put simply, it proved there's no general solution using radicals, roots and combinations of roots for polynomial equations of degree 5 or higher.
Degree 5, so quintics and beyond.
Exactly. Quintics, sextics, all the way up. Finding a single formula using just arithmetic and roots, like the quadratic formula we all learned for degree 2, that works for all equations of degree 5 or higher. Abel proved it's impossible.
Wow. So that's a definitive stop sign.
It was huge. It basically told the mathematical community, look, stop trying to find these neat, explicit, radical-based formulas for the general case beyond degree 4. And so classical algebra pretty much declared these higher degree equations But they have significant drawbacks, especially when you're dealing with those really high degree polynomials we mentioned, like 18th degree.
What kind of drawbacks?
Well, for one, they can be really sensitive. Tiny changes in your starting guess or small rounding errors during the calculation, which are inevitable with computers. Yeah.
والله امبارح شنو؟ امبارح خميس يمكن انا ماضي ساعه ما جيت هذا ولا في نص ما جيت هذا انا سيدي 5 المزومه صراحه 5 مش مثل المزومه اخر مره ما تقول لك يقعدوا يجيب قلت له خلاص يجيب قلت له لا 7:30 جاء ما بحاول الليل 9:30 طول تعطلت هذه تعطلت هنا باش ما تفتيش قبل تمرين الدنيا مبلعه ممكن يقعد في البراكسي في ساعه فور في وصلت لهنا خلاص لا والله لا يتعدى ممكن يتعدى البير شوي تقريبا هذيك ونص على اساس قلت اسمع فريق انا اسمع سيري بس
root of 2 plus the square root of 5 to give you a decimal number, usually.
And they can't like
سيدي
prove it's perfect. That's the other key bit, symbolic verification. An AI might give you an answer that's incredibly close, but it generally can't provide the mathematical proof embedded in the symbolic form itself, showing that if you plug this exact expression back into the equation, you get precisely 0. They struggle to capture that deep algebraic structure needed for exact radical solutions.
Okay, right. This is where it gets really exciting then, because all this Abel's wall, numerical limits, AI's approximation issue sets the stage for Ezouidi's theorem. You described it as a paradigm shift. What actually makes it so revolutionary? How does it get past these hurdles?
It's revolutionary because it tackles those limitations head on. First, and most importantly, Ezouidi's theorem delivers exact symbolic solutions. We're not talking approximations anymore.
Real provable answers.
Exactly. Precise mathematical expressions, often involving radicals, square roots, cube roots, potentially higher roots for degrees that were long considered impossible to solve this way, including, as you mentioned, specific types of 18th-degree polynomials.
Now, what's the mechanism?
It uses a novel, radical-based framework. The really fascinating part is how it seems to uncover hidden algebraic symmetries within these complicated equations.
Symmetries.
Yeah, think of it like finding a hidden pattern or structure within the polynomial's coefficients that wasn't seen before. This structure, these symmetries, allow the roots to be expressed using radicals, even for these high degrees. It's like finding a key that unlocks a structure we didn't know was there.
Okay, finding hidden patterns. And you mentioned something about structure.
Yes, another crucial element is its recursive structure. This isn't just a magic formula that pops out an answer. The theorem
Specific solvable cases within the general rule.
Precisely. It goes beyond Abel's wall, but revealing that the wall wasn't absolute for all specific equations, just for a single universal formula. It essentially redraws the map of solvability, showing there are large, previously undiscovered territories within the boundaries set by Abel where exact radical solutions exist. It significantly expands our understanding of algebraic solution theory.
Okay, so bringing this all together. For someone listening, maybe trying to make sense of complex data or find clear answers, what's the real takeaway here? Reshape.
Solutions hidden in plain sight.
That's a great way to put it. And that journey explored today from